Hey, good morning or good afternoon, honors physics students. This is Mr. Evely speaking to you. Just a quick introduction to a physics concept, an electrical concept known as the electric potential. Electric potential is a quantity. We use the capital V for its variable. Think about potential energy. Now, potential energy and potential are related to each other. And the best way to find an analogy that will fit is to look back at gravitational potential for just a second. Imagine we've got a physics brick on the ground here, and it's got mass m, and we lift it to height h. If we do that, we've changed its potential energy. We've taken it from what we usually call zero potential energy to a higher potential energy, or even if we don't call it zero, the change in the potential energy is mgh. Okay? Let's say I got a bigger physics brick, mass m, and we lift it to the same height. Okay? His change in potential energy was mgh. His change in potential energy, this guy's change in potential energy, is also mgh, except bigger mass. Okay? Now, what we can do is say that there's something about this level here that is independent of what mass that we place. That there is something not called potential energy, but something called its potential. Say that there are levels here due to the gravitational field, and if we lift something to a certain level, we have given it a certain change in potential. And the way we describe that, if it were gravitational potential, we would say the gravitational potential of this line relative to this guy would be the change in potential energy of an object divided by its mass. Okay? Now, if we did that, if we found the change in potential for this guy, we'd say, oh, well, its change in potential is going to be mgh over m. And if we find the change in potential for this guy, it'd be mgh divided by his mass, m. And we get the same answer. So in other words, in the field, there are levels that we could call just g times h, which we could define, if we wanted to, as the gravitational potential of each level. Now, we don't do that with gravity because we really don't need to. But we really could say that there is a property of the field, whether or not there's an object in the field or not, there's a property of the gravitational field which says that objects at certain levels will have different energies, different potentials, I should say, based on their distance from the ground. Now, that sort of helps, it sort of makes sense, but let's take a look at electrical potential now. Okay? Suppose that I've got a positively charged object which can't move. We'll nail it down, we'll keep it right there. There's an electrical field all around it. Okay? Let's say that I take a small positive charge, okay, I'll call the big guy Q, and I'll call the little guy little q, and let's say that this guy is the thing that's making our field. So this is kind of like the Earth here. The difference is electric fields, electric forces can repel or attract. So in this case, it'll be a little different than gravity because we've got repulsion. But imagine this guy has got this field in all directions. Okay? So if I decide I'm going to take this little guy and move it from, say, point A to point B, that's going to take some work on my part. Just like when I lifted the physics brick, I had to do some positive work in order to do that, and that caused a change in the potential energy. That's what's going to happen here. I've got to apply a force this way toward the positive charge in order to get this guy from here to here. Okay, so I've got to do some work. Now, the amount of work I do is equal to the change in the potential energy of this object. Okay. Now, if I have a little charge, if I put a little charge here and push him in, I got to do a certain amount of work, and his potential energy will increase by a certain amount. If I've got a bigger charge, I'm going to have to do more work, even though the distances are the same. Point A and point B haven't changed. If I've got a bigger charge here, I'll have to do even more work. Just like with the brick. If I've got a little brick, I got to lift him up. I'm going to do some work, which will equal his change in potential energy. If I've got a big brick, I've got to do a lot more work to get him up to the same height. But we said they had the same potential at that height. Okay, so what we're going to do is we're going to say, okay, well, the work done by me equals his change in potential energy, but his change in potential is equal to that change in potential energy divided by the charge. Okay, so if we take this little guy and we move him from here to here, I have to do positive work. Why? Because the force I'm applying is in the same direction as the displacement. I can't just say force times distance because the force is increasing as I push this guy from here to here. But I can say that the work that I did in getting him from here to here equals his change in potential energy. Now, if I've got a charge that's twice as big, that means I got to do twice as much work, and it'll be twice as much change in potential energy. Okay, just like this guy, if I've got twice as much mass, I'm going to have twice the change in potential energy. But if we divide by the mass, we have exactly the same potential. Same here. If I take this charge and I double it, I'm also going to get a doubling of the change in potential energy. In other words, the change in potential, V, from here to here is the same no matter what charge moves from here to here. Okay, so the potential difference between two spots in the field is the change in its potential energy divided by the charge. And remember, this guy is equal to how much work I have to do to get him from here to here. Okay, so potential is kind of weird. Think of it as the change in potential energy of a charge, or of a charged object divided by its charge. Okay. Couple of things you need to know about potential. Number one, it's not a vector. Okay, it's amount of energy per unit charge. Units, keep in mind, on the top here we have energy, so that's joules. On the bottom we have charge, that's coulombs. So the unit is joules per coulomb. And a joule per coulomb is called a volt, named after Alessandro Volta. So you recognize that, the unit of volts you see on batteries and other electrical devices. And basically what it does is it tells us how much energy is available per unit charge. So if you have a 9-volt battery and you hook a circuit to it, the available electrical energy is 9 joules for every coulomb of charge that passes through that battery. And we'll get more into DC circuits in the next unit, and this will make even more sense. So volt is kind of a very common term, but all it means is energy per unit charge. Okay. Something else we should take note of too is that in an electric field we can draw another type of line called an equipotential line. An equipotential line is a line that connects points of the same potential. So in other words, if I draw in some equipotential lines around my charged object, it means that I have exactly the same amount of work to move the charge from here to here as I would from here to here. In fact, the way the field works if I move it along an equipotential line, I'm doing no work. Its potential energy and its potential is remaining the same. In order to change its potential, or to change its potential energy, I have to move it from one equipotential line to another. So I move it off this equipotential line from here to here, I increase its potential. If I move it from here to here, I decrease its potential. But moving it along an equipotential line does nothing. I do no work. I do not change its potential energy. Therefore, I don't change its potential. Equipotential lines are always perpendicular to electric field lines. And again, no work is done as long as you stay on an equipotential line. Let's do a couple of mathematical examples and we'll bring this video to a close. All right, this is just an introduction, so a couple of simple calculations. Number one, what work is done when 3 coulombs of charge is moved through an electric potential difference of 2.5 volts? Okay, so we know that electrical potential difference is the change in the potential energy of the charge divided by the charge. So if I want to know what the change in potential energy is, I could say change in potential times the charge. Again, if I want to change the potential energy of an object by, say, 10 joules, I have to do 10 joules of work on it. So in essence, what we're figuring out here is how much work is done. The change in potential, it said, is 2.5 volts. The charge is 3.0 coulombs. Check out the units. This is joules per coulomb times coulombs. The answer is 7.5 joules of work. Okay, in moving this charge from one point to the other, it's increased its potential energy by 7.5 joules. Therefore, I had to do 7.5 joules of work. Example 2, how much kinetic energy is gained by an electron that accelerates through a potential difference of 1 volt? Okay, so let's say I've got a negatively charged surface here and a positively charged surface over here. Let's say the potential difference between these two surfaces is 1 volt. If I take an electron and set him right here, he's going to fly over to the other side. In essence, what happens is he loses some potential energy and it turns into kinetic energy. So this is kind of a law of conservation of energy thing. So we say, okay, well, how much potential energy does he lose? Okay, like we said in the last problem, delta V equals delta U over Q. So delta U equals delta V times Q. So how much does he lose if he drops through 1 volt potential difference? We know the charge on an electron is 1.602 times 10 to the negative 19 coulombs, and it's negative. So if he loses negative 1.602 times 10 to the negative 19 joules of potential energy, that is a gain of 1.602 times 10 to the negative 19 joules of kinetic energy. Now, particle physicists actually use this unit to measure the amount of energy for a particle, because many particles have the charge of an electron or multiples of the charge of the electron. So they call this unit of energy 1 electron volt. So the electron volt is a unit of energy equivalent to 1.602 times 10 to the minus 19 joules. It's the amount of energy, kinetic energy, gained by an electron when it falls through a potential difference of 1 volt. All right, final example. Suppose we have a pair of parallel plates that are separated by a distance of 2 centimeters and given opposite charges until the potential difference between the plates is 50 volts. Now we're going to take a look at this later in the chapter. This is a device called a capacitor. So imagine I've got two metal plates, okay, side by side. We make this one really, really, really positive, and this one really, 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 really negative. The distance between them is 2 centimeters, or 0.020 meters. The potential difference between the two plates is 50 volts. And the electric field between them, remember electric fields go from positive to negative. The electric field between them is kind of strange because it's uniform. Notice that the lines are parallel, they're not getting further apart or closer together, so that means everywhere in between these plates, the electric field is exactly the same. In real life, that's not exactly true. There's always some fringing on the ends that kind of curves out, and the electric field isn't quite uniform, but deep inside the field between the two plates is very, very uniform. So, if we say that the potential difference between the plates is equal to the change in potential divided by the charge, what we could do is say, well, the change in potential is equal to the work done in moving a positive charge from one plate to the other. If the field is uniform, we can get away with saying, hey, that's force times distance. Okay? Because if the force is constant between the plates, we can get away with work equals force times distance. And the amount of work we do is equal to the change in potential energy of the charge. If I take this guy, you remember this is actually the definition of electric field. So if the force is the same on the charge everywhere between the plates, I can say it's the electric field strength times the distance between the plates. That means the electric field between the plates is delta V over D. So we've got 50 volts potential difference. The distance between the plates is 0.020 meters, which means that the electric field strength is, I believe, 2,500 newtons per coulomb, or notice another way of saying it is 2,500 volts per meter, which is a different set of units, but it means the same thing as newtons per coulomb. So quite often, if you look in textbooks, data tables, you'll find volts per meter instead of newtons per coulomb as the units of electric field strength. Okay, this stuff is kind of strange, and I realize I can't cover everything as effectively in a video lecture as I can when I am here answering your questions. But hopefully this will get you moving in the right direction and helping you to solve a couple of problems while I'm gone. When I get back, we can review some of these concepts. So don't be frustrated, do your very best, and I will see you soon.